All right. Hello, everyone. I'm going to go ahead and begin our test review. So I am recording this to post for everyone else on YouTube, for those who can't watch right now. So keep that in mind. You're feel free to talk and ask questions or type questions in the chat if you have any questions. So with that being said, any questions before I begin the content review? I'll go ahead and say the format's the exact same as previous tests, probably about the same distribution of questions as well, being multiple choice and free response. So all that's the same, format's all the same. Any questions? Okay, it doesn't look like any questions on format. So let's go ahead and dive right in on the review. And as with the previous reviews, this is not, I'm not going to lecture too much about the material. I'm just going to kind of say what I expect and maybe kind of help narrow your studying a little bit as we get close to the test. So first section on the test is 10.3, which was our introduction to polar coordinates. So you need to be comfortable with polar coordinates, graphing polar coordinates. Okay, so I'll say we need to be able to graphing polar coordinates. Converting back and forth between polar and Cartesian. And then also something we did on the homework was we had one set of polar coordinates, and remember the idea that, okay, these polar coordinates are not unique. If I have this point in polar coordinates, maybe that's 1 pi over 4, okay? But I could also write that in a different way. I could write that as what? -1 5 pi over 4, okay? So this idea that there's more than one way to write the same point in polar coordinates, keep that in mind and review that. So I'll kind of say the multiple forms of polar coordinates. Okay. So I wouldn't worry about, let's see, 10.3 also had like derivatives of like polar functions. Do not worry about the derivatives. In section 10.3, apparently, since it wasn't on the homework, I was told it shouldn't be on the test. So this is really everything from 10.3 that could be on the test. Okay. Any questions? All right. Oops. Well, will you have to sketch? I'll go ahead and say no. No, I've written the test, so I know it's on there. I'm just deciding whether or not I should tell you guys, but I'll go ahead and say that no, you won't have to sketch anything for polar coordinates on the test. In fact, let's see, I don't think there's shouldn't be any sketching at all. Yeah, no sketching. Oh, so I'm not sure everybody can see the question. I don't think you guys can see each other's questions. So I'll say, one of you asked, will we have to sketch, like in the free response questions, referring to the polar coordinates? No, you won't have to sketch any of the polar coordinates, polar graphs. Like I said, know these three things, just kind of the equation stuff, maybe converting between polar coordinates. I would say sketching, you won't have to sketch for the answer, but I will say sketching can be very beneficial, especially really for all, well, I guess, okay, so I guess this won't be on the, I've kind of eliminated this from the test. But I would say sketching is still very beneficial for these things. It kind of tells you whether you've done it right or not, because like if I give you the point, what, like 4, right, in Cartesian coordinates, and I tell you to convert to polar coordinates, and you get some answer, right? So maybe you convert and you get the answer. Let's see. Maybe you get like 4 and then negative pi over 3 or something, right? Maybe you get that answer somehow. And then you could check your answer by graphing, and you say, okay, well, 4 negative pi over 3, that'd be like down here. And then you see that's obviously not the same point you started with, so maybe that's a clue you did something wrong. So I think it can be beneficial for like checking your work. And maybe even more so in this second point. Okay, graphing the points would be a good way to check your work, but it won't be necessary for full credit. I'll say that. Moving on to section 10.4. I think, there's not too much to say about the 10.3. These topics, it's fairly straightforward. You can see the video for that. Okay, 10.4, what is in 10.4? Areas and lengths and polar coordinates. First of all, I'll go ahead and say we don't have to do, I don't think we even covered it in the lecture, but we don't have to do, any arc length for polar coordinates. I can't remember if we did this or not. I think this did end up appearing on the homework maybe, but we don't have to do any arc length for polar coordinates. So all we need for polar coordinates is areas, okay, for 10.4. So remember the formula, okay? If I have r as a function of theta, this polar equation, and I want to find the area enclosed by the curve in between two angles, like for theta between, A and B. What is that? That's going to be the integral from A to B of 1/2 f theta squared d theta. Okay, so remember your formula. And then the only difficulty might be maybe you're not given these bounds, right? Okay, maybe you're not given this A and B. Maybe the question is phrased like, find the area of an inner loop or something. Of a curve, r equals what? 1 plus like 4 sine theta, something like that. Where maybe it's, I don't even know if I've got the curve right, but maybe it's one of these curves with like a kind of inner loop, and you have to find just the area of that bit. So how do you do that? You have to find those those intercepts. Okay, so maybe if you have a curve like this, I think this would be like something like, yeah. So maybe like r equals 1 plus 4 cosine theta would look something like this. It would give you one of these, what are they called, limicons, I believe, where you have this outer loop and inner loop, and you got to find, okay, where does this inner loop begin? Okay, and actually it'd probably be, let's see, 4 cosine theta would be hard. Maybe it's 2 cosine theta. Okay, so you gotta figure out when does this curve pass through that intersection, that origin. So you would set 0. Okay, this intersection is when the radius equals 0, right? So you would set 0 equal to 1 plus 2 cosine theta, and then solve for theta essentially. You get -1 equals 2 cosine theta. You divide both sides by 2. And then you ask yourself, okay, what angle has a cosine of -1/2? And that gives you a couple of answers, right? It gives you, let's see, like 2 pi over 3 and what, 4 pi over 3, something like that. And you see those are two angles where this curve intersects the origin. So maybe at 2 pi over 3, I'm here. That's where I first intersect that origin. And then I continue around this way. And then at 4 pi over 3, I'm back to that origin. So that tells me this area would be the integral from 2 pi over 3 to 4 pi over 3. And then the rest is just my formula, 1/2 times f theta squared d theta. Okay, so be able to find those bounds of your integral. Okay, and probably, let's see, limicon might be at the kind of higher end of the difficulty. What you might very well see is like one of the roses or clovers or whatever they're called, where you have some graph like this. The graph ends up being like a kind of 4-leaf clover or something like that, and maybe you're told to find the area of one of these petals or something like that. So you have to do a similar procedure where you have to find, okay, where does this petal begin and end, and so on. So that I would say is the major difficulty from that section. Any questions on 10.4? Okay. Moving on to section 11.1. So 11.1 is all sequences and kind of begins our material about series, things like that. So let's think about what we need from section 11.1, looking at the book. I would say you should be able to look at a sequence and write a formula for it. So maybe 4, 16, 64, and so on. Maybe you see, hey, that's the powers of 4. So the sequence will be like 4 to the n, something like that. And this is a pretty easy one. Maybe it's, you should know how to deal with the alternating terms. So if I have a sequence like -1, positive 2/2, -3/4, positive 4/8, and so on. Maybe you say, hey, okay, I got an alternating sign, right? And I'm starting on a negative. So that should probably be n if I want to start my sequence at 1. And then what's going on in my numerator? Well, let's see, I got 1, 2, 3, 4. Okay, so that's just n. And then on the bottom, I got 1, 2, 4, 8. So it's doubling every time. So maybe I say 2 times n minus 1, something like that. Or maybe how could we deal with that? Because if we do, let's see, 2 to the n, it would be 0 in that first term. How about 1 plus 2 to the n minus 1, something like that. Okay, so and there's usually a couple ways to write the same sequence. So a couple right answers. I would always say once you come up with a formula to double check your answer. 2 to the n minus 1, yeah, that would work. Yeah, so we could also do 2 to the n minus 1. Yeah, perfect. So there's usually a couple ways to write the same answer. So once you get a possible answer, just plug in a couple n's and double check your work. Once I have this kind of suspected answer, I plug in several n's. Okay, first one will be 1, and then then I have positive 1, and so on. Okay, which matches up with what I have in my original. Okay, so that works. So just double check your work. As far as let's see, any other things from 11.1. So 11.1's got a lot of material as far as like, okay, we got the monotone sequence theorem, things like that, where if we have a bounded increasing sequence, it's got to converge. That stuff's good to know. And in general, I'll say you don't have to know any of the specific names of the theorems, but you got to be able to tell whether a sequence converges, and more importantly, you might be asked to find the limit of a sequence. So just those basic limit techniques, like if I have, a sequence like 2 to the 2 times n over 3 and maybe something slightly more complicated like this. Okay, the limit of this is still just 2/3. Okay, because what's really important, it's these highest powers of n. Okay, so the basic techniques of finding limits of fractions, especially fractions where we have like a polynomial over polynomial. The idea that we can take, if I have a sequence that looks like kind of like a function of n. So let's say I have my sequences, let's say sine pi over n. Okay. And I want to find the limit of this sequence. Remember that if I have a continuous function, okay, since sine is continuous, I can take that limit inside the function. Okay. Then the limit of this piece, that's easy, right? The limit of pi over n as n goes to infinity is just 0. So my limit of this thing is going to be 0. Okay. So that's a very useful technique to know. And then we begin the series stuff, which will be really the meat of the remaining portion of the semester, excuse me. So the entire remainder of the semester is all about series in one form or another. So we start our first taste of series in 11.2. Definitely know that what's the definition of convergence of a series? You know, if a series is going to converge, you know, to find out if it's going to converge, we kind of think about it, at least in the back of our heads. We have this idea of the partial sums, the series of partial sums, or excuse me, the sequence of partial sums. So instead of considering an infinite series, we consider that finite series, okay? And we add up the first n terms and we get this sum Sn, and then all these Sn's give us a sequence, right? And then if this sequence converges, then we say the series converges. Okay, so a very important concept. 11.2, we also have, let's see, we have the basic series, right? We have our geometric series. Right. Oh, and I wrote it as a sequence. We have our geometric series, and then we have our telescoping series, right? And these are our two basic types of series we can find the sums of. Really, these are going to be the only types of series whose sums we can find in this course. Every other series, we're just going to figure out whether it converges or diverges. But for these two types of series, we can figure out the sum. So remember how to find the sums of each of these. And in particular with the geometric series, you know, we have this formula, right? Where if the geometric series is in this nice form, our sum is going to be what? A over 1 minus r, okay? But that's if our series is starting at 1 and our power is n minus 1, okay? What if our series is starting at 1 and our power is n? Okay, this would change the series a little bit. All right, so there's, you know, you need to be able to convert between, I'll kind of show you what I mean for a second. We need to be able to convert from this form here to the form whose formula we know, right? We have the formula for a to the r n minus 1, right? So how do we get from n to n minus 1? Well, this thing is the same as a times r to the n minus 1, right? And now we just kind of consider this as our new a. So the sum of this series would be a times r over 1 minus r, right? Okay, so a nice little trick to kind of play with the the power of our geometric series to make it match the form we need for our formula. Okay, any questions on that? So I'll just kind of stress again that when you see a geometric series, and maybe I'll ask you to find the sum on the test. Make sure that the form of this geometric series matches the formula you have for the sum. Okay, and in particular, make sure this matches and make sure this matches. Okay, if not, you need to modify that series a little bit to get it to match your formula. Okay, any questions there? Okay, not seeing any questions. So what do you do if n does not equal 1? Okay, somebody asks, okay, what if you get a geometric series and n does not equal 1? Let's say it's 2. Okay, this may or may not come up on the test. I won't say it won't, but let's see. This is actually a useful technique to know. You'll need this definitely in later courses and probably in the remainder of this course. Okay, so let's say I have, and this works for any series, it's not just geometric series. Okay, so let's say I have like a series starting at 2 and my stuff inside, let's call it just Bn, the Bn's. What if I want to kind of rewrite the series so it's starting at 1? Okay. So what if I want to change this so it's starting at 1? I can do that. That's fine. Basically, what I do is I subtract 1 from this to get it starting at 1. Okay. If I subtract 1 here, I add 1 here. Okay. So it would become Bn plus 1. Okay. So to see a concrete example, let's say I have like 4 times 1 over 2 to the power n minus 1, starting at 2. Okay, now I want to rearrange this to get it starting at 1. Okay, so I want this part starting at 1. Okay, so I subtract 1 here, and then I add 1 inside. Okay, and you might be saying, okay, but I can't use the geometric, I still can't use the geometric formula on that. Well, now once we have this part at 1, then I can just do my other trick of saying, okay, 1/2 to the power n, that's the same as 4 times 1/2 times 1/2 to the n minus 1. Okay, so you could do that sort of thing. Any other questions? Okay. All right, so let's move on to 11.3. So 11.3 is integral test, p-test, and estimating sums of the series. First of all, we don't have to estimate sums. Okay. So don't worry about estimating sums. What you absolutely have to know is p-test and integral test. And really the p-test is p-test is just kind of a special case of the integral test. So let's look at the criteria for the integral test real quick. Because if you're going to use the integral test, if you're going to use this integral test, and really if you're going to use any series test at any point, yeah, always have to verify the conditions of the series. So let's look at the integral test real quick. Remember what the integral test says. Okay. Okay, so it says, suppose f is continuous, positive, and decreasing on the interval 1 to infinity, and an equals f of n. Okay. Then the series a of n is convergent if and only if converges. So what does this mean for you? Okay, let's kind of translate this real quick. You have a series, okay, from 1 to infinity, and you see that the series is it kind of looks like a function, right? Let's say you have that's a good one. Okay. You have, oh, and this should be ends. Let's say you have this series, and you think to yourself, hey, ln is a function, right? So this function happens to, it matches up with a function of x, right? We could think of this as a function. We could think of, instead of ln of n, we could think of ln of x over x. Okay. And then we could think about this improper integral instead. So we're starting with this, and we say, hey, that kind of reminds me of this function ln of x over x, or we can make a function out of it. As long as these conditions hold, right, we can use this theorem to tell us whether or not this series is convergent. Okay, so what do? First, I need to check these three things. Okay. So I check each of these three conditions, and I need to do that if I'm going to use the integral test. So first of all, I need to verify that this is continuous. Okay, so ln of x is continuous. Where is it continuous? On 0 to infinity, for sure. X is continuous everywhere. So ln of x over x. Let's see, this is continuous as long as x doesn't equal 0, right? So it's continuous on 1 to infinity. Okay, so it's continuous. And if you just want to give a little argument like that, that's fine. Okay. 2. How do I, well, is it positive? Well, actually, let's see, this actually wouldn't be positive on 1 to infinity, but let's say my series started at 4. Okay, then everything's hunky-dory, you know. Okay, so positive, let's see, I could say something like ln of x is positive on 4 to infinity and x positive on 4 to infinity. So ln of x over x positive 4 to infinity. Okay. Lastly, we need to verify that this function is decreasing. Isn't ln of 3 1.09? Yeah, it's that's fine as long as it's positive. It doesn't matter. I'm not saying, I didn't say what it equals. I'm just saying it's let's see. Yeah, so yeah, it would be, we could, we could use 3 to infinity instead. I just didn't want to think about it too hard, but it's definitely positive on 4 to infinity as well. And then we need to verify it's decreasing. So how do I, and this is probably the hardest part of showing these 3 conditions. How do I show that this function is decreasing? Okay, well, if it's differentiable, meaning if I can take the derivative of it, what I do is I take the derivative and then show the derivative is negative. Okay, so what if this is my f? Okay, what's the derivative of f? What's f prime? Okay. Well, it might help to rewrite this as ln of x times x to the negative 1. Okay. Now, what's the derivative of f? Let's see. This is product rule, right? 1 over x times x to the negative 1 plus ln of x negative x to the negative 2. Okay. Okay, so this is the derivative. Now, on the interval 4 to infinity, or, we could do 3 to infinity, okay, ln of x is greater than 1, okay? So this top part will be negative, right? And then we're dividing a negative by a positive number. So that derivative is going to be negative on, we're using 4 to infinity. So that derivative is always going to be negative on 4 to infinity, meaning on that interval, my function's always decreasing. Okay, so I've verified, I could say something like, since f prime is negative on 4 to infinity, f is decreasing on 4 to infinity. Okay. So as I said, this verifying it's decreasing is probably the hardest part. Okay, we just need to take the derivative of our function and then prove that derivative is negative. Okay, and in your test, if you get an integral test problem, it'll be a differentiable function. So don't worry about when the function, if the function is differentiable, everything you see will be differentiable. Okay. And then once we satisfy these 3 conditions, we're not done yet. Once we satisfy these 3 conditions, that just gives us the ability to look at this integral instead. Okay, so now I need to be able to find this improper integral, and I need to do this properly, right? So since it's going to infinity, first thing I need to do is I need to do my improper integral correctly. So first thing I do is I write it as a limit, right? And then I solve the integral. This is like a u sub. Okay, and this limit goes to infinity. So this improper integral diverges, right? Which means my series will also diverge. And then I need to have some sort of wrap up sentence, I would say. Since 4 to infinity of ln of x over x dx diverges, the series ln of n over n diverges by integral test. Okay. And this kind of shows a point that I want to hammer home to you guys, that whenever we use a test, okay, we need to state the test. Okay. It's not enough to just say, you know, if I had done all this work and just said, okay, if I just said diverges, I'm going to lose some points, right? Even though like I might know you're using integral test here. Okay, this is a lot of work. That's obviously integral test, right? So it's pretty clear you're using integral test. But there's a lot of other tests that it might not be so clear what test you're using. So you need to always state explicitly what test you're using. So just do that with every problem, okay? I know some of you guys aren't used to writing so much, like so many words with your math homework, but get into that habit, because the more math, the higher in math you go, the more words you're gonna have to write. You know, my work looks like just essays. You know, there's not, you know, very many of these kind of equation type things. It's all words, so you got to get used to that. All right, any questions on integral test? All right. In 11.3, we also had the special case of the integral test, which I call the p-test. So if we have a series of this form, 1 over n to the power p. Okay. This series is going to converge if p is greater than 1, right? And it's going to diverge if p is less than or equal to 1. So this is a great test to know, because really if you get something like this, if you get like a p series, if you get something like 1 over n to the 0.0963, something like that, maybe it looks kind of intimidating, but it's really simple to check whether this converges or diverges. You just say, okay, 0.0963 is less than 1. So you should say this, this diverges. Let's look at the exact name of the series if it even has one. I just always call it by p-test, but maybe there's a better name for it. You could just say by theorem on convergence of p series. You can say, for my test, you can say by and really, I think this is acceptable for everybody by p-test. This is kind of universally accepted terminology, so I think that's fine. But again, we see this theme that we have to state what test we're using. All right, any questions on p-test? All right, well, let's see. I think that covers, let me just look at what look at my test that I've written for you guys. I'm not going to tell you what's exactly on it, but let me make sure I haven't forgotten to cover any major topics. Let's see. Oh, yeah, there is one other thing I wanted to mention. Let me make sure that's the only thing. Okay, I thought of a couple other things to tell you. First of all, p-test only works in this. It has to look like this, right? It can't be, it has to be 1 over n to the power p, okay? It can't be anything else to the power of p. It's got to be just that 1 over n, okay? Maybe we could have a constant outside, maybe we could have like a times 1 over n to the power of p, something like that. That's fine. But, okay, we can't have, I don't want to give away too much, but just be careful what you're considering a p-test, all right? P-test refers to a very specific thing. All right, so that's one thing I wanted to mention. When you see on a problem, if you see something like the phrase in the setup of the problem where it says, verify all hypotheses and show all work. This is a common phrase to see, is verify all hypotheses. That's a common phrase to see with the series questions, because a lot of these series questions, if we go back up to the integral test, the integral test had these 3 hypotheses, right? It's the function, that function is going to be continuous, positive, and decreasing. So we got to verify, those are, hypotheses. We got to verify all those hypotheses, which is what I did in my work here. I verified all those hypotheses. Okay. So that's a clue when you see that in a question. Okay, I got to do some work here. I got to show some of these hypotheses. So since this is like an open book test, you should be able to go look at your integral test and see what the hypotheses are and remember how to verify those, etc. Okay, so that's one other thing. And then one other thing I forgot to mention that's huge is the divergence test, right? Which we learned in section 11.2. Definitely know the divergence test. And I would say, and if you're testing a series for whether it converges or diverges, maybe that should be the first thing you look at. So if I look at a series, maybe I see a series 3n squared plus 7x over 4n squared plus 9, and I'm trying to test this for divergence, and I say, okay, what test do I use? Well, maybe the first thing I should do before I even start thinking about more complicated stuff is divergence test, right? I look at this stuff inside my series. I call that my AN, okay? Remember what the divergence test says. If the limit of AN does not equal 0, then the series diverges. What I want you to be careful of, though, is reading too much into the divergence test. This is all the divergence test says, okay? Okay, so if the limit of an does not equal 0, the series diverges. If anything else is going on, we don't know what's happening. So like if I have a series, okay, and okay, this is my an, right? Well, in this case, the limit of an does equal 0, right? But this is the harmonic series. It still doesn't diverge. I mean, it still doesn't converge. It diverges, right? So just because this limit equals 0, that doesn't necessarily mean the series is going to converge. So you should never have the phrase, you should never say something like converges by divergence test. This is not a thing, okay? Don't do this. Super bad. Okay, the divergence test can only tell us if something diverges. That's all it can tell us. It can never tell us if something converges. If the limit of the stuff inside, if that limit of an equals 0, it could still diverge. You know, the divergence test, if the limit is equal to 0, the divergence test is just inconclusive. We have to do other tests to figure out if our series converges or not. So that's a huge point. Is there any shred of doubt on that? That's a huge point to know. Okay, no, well, I'm still kind of confused with the test. Okay. Is that with the divergence test in particular? Right. Okay. So let's since the divergence test is so important, let's talk about this a bit more. Okay. So we have a series, right? And we have this stuff in these terms inside. Okay. There's two possibilities for the divergence test, right? Okay. If the limit of the stuff inside, if the limit of these terms, okay, does not equal 0, then my series diverges. Okay. If the limit does equal 0, we need to do more tests. Okay, we have to do something else besides the divergence test. Okay. So that's why I'm saying the divergence test can really only tell us if something diverges, right? If the limit doesn't equal 0, if the limit of the stuff inside doesn't equal 0, the series is going to diverge. If it does equal 0, then we got to do some other test. Okay, so an example. Excuse me. Okay, so an example. We could use that 1 over n thing again. Okay. So I look at this series. Yeah. So this person said, okay, so you should just use the divergence test to see what you should do next. Yeah, exactly. So like this series would be an example, right? Like this is my series. So my ANs are 1 over n, okay? And clearly the limit of AN equals 0, okay? So that just means, okay, the divergence test doesn't tell me anything. Now I got to go further. And I could, you know, moving on to my next step, this is technically a P series, right? With P equals 1. So I could say, okay, 1 over n diverges by P test because P equals 1. Okay. Another example. Let's say I had, let's do a couple examples. Okay, so let's say I had 9 over 8 to the power n minus 1. So this looks like a geometric series, right? But you know, you could use the geometric series test and say, okay, R is greater than 1, so it's divergent by geometric series test. Or you could say, well, hey, limit of 9 over 8 to the power n as n goes to infinity. Well, that limit's equal to infinity. which is not equal to 0. So the series diverges by divergence test. On the other hand, if you had a series like 8 over 9 to the power n minus 1, maybe maybe you don't realize it's a geometric series test at first. So you try the divergence test, and you say, hey, okay, what's the limit of this? And then you realize that this limit equals 0. So the divergence test doesn't tell you anything. So that just means you have to dig a little deeper. You got to try something else, and maybe you look at your textbook, and then you find the geometric series test, and you say, hey, this thing's a geometric series, so it's going to be convergent. All this told you is that you have to dig a little deeper. And then you go on to find this. Okay, hopefully that was helpful. Any other questions on divergence test? Okay, I'm not seeing any other questions. So will harmonic series be on the test? Yeah, harmonic series is kind of like a classic example of a divergent series. So I'll say all of you guys should know that this series 1 over n is divergent, okay? And it's kind of so fundamental. I won't say easy, because maybe, you know, it is kind of strange that this thing's divergent, but something like 1 over n squared, that's convergent. Okay. But I would say if you're going to memorize kind of like one example of a divergent series, you should know that this thing is divergent. Okay. So can I go over? Yeah. Somebody else asked for a telescoping series question. But as I was saying about this, you should all memorize that this is a divergent series. This is good to know. Like I said, it's kind of the classic example of a divergent series. Okay, so let's kind of circling back to 11.2 a little bit. Remember, I said that there were two things, two types of series we could find the sums for, right? The geometric series and these telescoping series, which kind of look like this, some version of this. So telescoping series are kind of in their kind of most natural form, they're easy to recognize. Okay, so I'll say like this would be a telescoping series, and they all have this kind of basic form where you have inside the series you have this like subtraction, you have like something minus something. Okay, and then if you the kind of gist of the telescoping series is that when you write out the terms, you're going to get a lot of cancellations. So just like write out several terms of this, or kind of think about what several terms of this would look like. Like if I plug in 1, all right, the first term would be 1 over 1 minus 1 over 2, right? And then I add to that the next term, which would be 1 over 2 minus 1 over 3. And then I add to that 1 over 3 minus 1 over 4, okay? And so on. And then if I kind of drop all the parentheses, right, I would see that there's all these cancellations. You know, this would cancel with that. Minus 1/3 would cancel with plus 1/3, and so on. So if I consider like the first n terms, if I add up like, you know, or let's say the first k terms or something like that, what would I end up with? I would end up with 1 and then everything else would cancel in the middle, right? And then I'd have what? Oh, 1 minus k plus 1 or something like that. Okay. Right? So that's what my sum would be if I added up the first like k terms. And then the limit of this thing goes to 0. So my series should converge, and it should converge to just 1. Okay. So how I would say to deal with that is, if you have a telescoping series and you recognize it as a telescoping series, let's say it's a bit different. Let's say it's like 3 over let's say it's a little bit different. Okay, so maybe I see this and I feel like it's a telescoping series. Okay, because I got this it kind of looks like my previous example of the telescoping series, right? It's a similar form. So I would start by writing, if you have that suspicion, write out several of these terms. So if my series is starting at 1, let's just verify that this is I just kind of made this up on the spot. Let's make sure it is a telescoping series. So I plug in a couple n's, right? Okay, so the first term would be 3 over 2 minus 3 over 2 times 2, so 3 over 2 times 2, which is 4. Okay. And then I would add, let's see, 3 over 2 times 2 minus 3 over 2 times 3. So yeah, it looks like a telescoping series, and that a lot of this stuff is going to cancel, right? And then I expect this is going to cancel, blah, 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 blah. Okay. What you need to do is verify that like this stuff that's going to be left over, like if I added up the first 3 terms, okay, the next term would be what? Okay, this is canceled with this. So if I added up the first 3 terms, I would have 3 over 2 minus 3 over 2 times 4, which is 3 over 8. Okay. What I need to do is I need to verify that this leftover term is going to 0. So how can I write this leftover term? That's, if I add up the first 3 terms, it's 3 over 2 times minus. Okay. So this is how I could write my sum, right? I'm always going to have this 3 over 2 at the beginning, and then I'm subtracting away this 3 over 2 times n plus 1. This term's going to 0. So my sum is going to 3 over 2. So how I would deal with these telescoping series is, if you think something's a telescoping series, write out several of the terms and see what's canceling and see what you're left over with. As long as that term that you're left over with is going to 0, your sum is just going to be whatever you start with, your first term, okay? The trick with these is that sometimes it's a telescoping series, but it doesn't really tell you it's a telescoping series, right? Like maybe you have 1 over n, I forget the exact example, but I think in the homework there was an example like this or something like that. And you use partial fractions decomposition to kind of write it as something like this. You know, I'm sure my math is a little messed up here. And then this is a telescoping series, right? So the trick is it had 2, like it was it this, something like that? Yeah, yeah, okay. So if you write it like, if it's a 2 on the top, then it decomposes into this thing, right? And then, you know, the trick is how do you recognize that this turns into this. Well, you're not going to have a problem like that on the test. I'm not going to give you anything that complicated, okay? So if I give you a telescoping series, it's going to be easy to recognize. It's going to be something like this, or, you know, at the outside, maybe something like that. It should have that nice subtraction where you can look at it and say, hey, I got this subtraction. That's going to give me a lot of cancellations. That's probably a telescoping series. I'm never going to give you something like this on a test. So hopefully that kind of helps you on the telescoping series bits. I wouldn't worry too much about it, but yeah, just the basics of it. Okay. So I think I've covered all the material I want to cover, and now it's all what you guys want. I'll kind of open it up to you guys for questions on any topic. And if you're all set, you can sign off if you like, and I'll hang around for a few minutes and answer any questions anybody has. And how's the my family's great, thank you. Baby's doing great. She's beautiful. You guys want to see her? I'll show her off if you want me to show her off. Baby's name is Josephine. Yeah, so we're calling her Joe for short. Josie, but yeah, she's adorable. Let's see. Here she is, baby Josephine. She's a lot better looking than I am. Thank you for asking. I'm always happy to show her off. Thank you very much. She is cute. Yeah, so I'm back to making videos. I made videos for this week's lectures, and I don't anticipate any more interruptions in my lectures. So it should be me for the rest of the semester. Hopefully you guys liked Ariel's videos as well. She's great. I used her videos a lot last semester as well, kind of when we switched to virtual. She had a better setup than I did, so I relied on her a lot. But yeah, I'm back to making videos now. You can still follow, like, if you prefer Ariel's videos. I think she has chapter 11, like from section 1 up to section 11.6. So if you go and click on the old links and kind of look at her YouTube channel, you can see her videos if you like. I won't be offended if you go and look at her videos. Okay, somebody asked, can you explain how to find A and R values in geometric series? Yes, I can. Okay, so a geometric series should be fairly easy to recognize, because the only time you should see an n is an exponent. Okay, so let me stick with this. So if you're looking at this series, notice that the only time we see n inside the series is in this exponent right here. Okay, and that should be a clue. So for example, and I will go ahead. Yeah, I'll go over how to rearrange the series as well. We'll go over this step by step. Okay, so I have a geometric series. So for example, if I had if I had something like 8 times 1 over 2 to the power n minus 1. Well, I see I got the only time an n appears is in this exponent here, and everything else is constants. Okay, so that's kind of a common layout for the geometric series. Now there are kind of ways that it might be disguised, right? Like instead of having it like, you notice these two are very similar, where I have like this A out front, and then I have the R, and then the n minus 1, right? First of all, before I move any further, I'll say the R is always going to be the thing to the power, okay? So notice there's the R here is to the power n minus 1. Okay, so that's telling me this thing is the R. This 1/2 is the R. Okay. So when I plug that into my formula where the sum is A over 1 minus R, okay, I know this 1/2 should be my R. And then what else is there? There's this 8, right? So that should be my A. As long as I have the right layout of my series. Okay. So that should be fairly straightforward, but as I said, there are some ways to disguise it. So maybe instead of having it laid out really nicely, where it's like 8 times 1/2 to the n minus 1, maybe it's something a bit trickier, like 8 over 2 to the n minus 1. This is the same thing, right? These series are the exact same. And what I could do is, whenever I have, maybe if it's unclear, maybe if I have kind of a suspicion it's a geometric series, or maybe I can even tell it's a geometric series, but I can't quite figure out what my A and R are, try and kind of rewrite it in this form, okay? So how could I modify this bottom thing to get to the top thing? Let's kind of get rid of this stuff in the middle. Okay. Well, first of all, I could pull the 8 out front and then write this as 1 over 2 to the n minus 1, right? And then 1 over 2 to the n minus 1, that's the same thing as 1 over 2 to the n minus 1. So that you can use that kind of trick to try and modify things to modify how your series looks, to make it a bit more obvious, such as geometric series. Now let's talk about, first of all, is that helpful for the person who asked how to find A and R values? Is that make sense? Is that helpful? Okay. Let me know later if you have any further questions on that. So now let's talk about, okay, what if, our formula for the sum of a geometric series is very dependent on how it looks, right? I believe in your textbook, what they give you is this formula. If you have the form A times R to the n minus 1, the sum is going to be A over 1 minus R, right? That's if, remember, that's if absolute value of R is less than 1. If the series is convergent, then the sum is equal to this. Hold on one second. Okay. All right, as I was saying, so the sum is very much dependent on the exact form of the series. So this formula doesn't work if instead of like n minus 1, we have n. There's a different formula for that. You can look that up on Google or something like that. I think you just end up subtracting A from it. I think the sum ends up being like, or do you add A to it? I forget. Let's see. Yeah, you subtract 1 from it. So if you have A to the R n and starting at 1, the formula for the sum becomes A over 1 minus R minus A, I believe. So different formulas, right, depending on the form of the series you have, okay? If you just want to memorize one, okay, which is usually, that's kind of, I try and memorize the least amount of formulas possible, right? If you don't want to memorize this additional formula, what do you do? What do you do when you're kind of given this wrong exponent here, okay? There's this trick. What you're going to do is just, you're going to split off one of those R's. Right? R to the power n is the same thing as R times R to the power n minus 1. So now you have this geometric series, okay? And just consider this A times R, just consider that as a new constant B, okay? So basically what you have is a geometric series B to the R minus R times n, R to the power n minus 1, okay? And now you can use your familiar formula, right? The formula, the sum of this series is B over 1 minus R, okay? So an example, let's do an example. I find a concrete example is always the best way to explain something. Let's say I have 3 times 5 over 6 to the power n. It's starting at 1, going to infinity. So this looks like a geometric series, right? And maybe it's clear now that this is my R, and this is just some constant A. So I want to use this formula A over 1 minus R, right? But for that formula, I need n minus 1 here. So I don't have that, right? So I can't use this formula directly. So what I do is I say, hey, this is the same as 3 times 5 over 6 times 5 over 6 to the n minus 1. Okay, and now I got an n minus 1 there. Okay, so that's good. And now what I could do is I could just multiply this out, right? And I could just rewrite what's 3 times 5 over 6. That's 15 over 6, right? And then I got 5 over 6 to the n minus 1. And now everything's in my good formula. You know, I got the n minus 1 here. I got the n equals 1 there. Now I can use the geometric sum, the formula for the geometric series. So my formula is 15 over 6 times 1, or excuse me, over 1 minus 5 over 6, which is what? 15 over 6 divided by 1 over 6, which is 15. Okay. Does that make sense? Does anybody have any questions on how to kind of convert between those two forms? Okay, good on that one. Okay, I will now open the floor back up to any questions at all. Anybody have any questions on anything? Okay. Nobody's asking any questions. So again, feel free to sign out whenever you like. I'll hang around until, you know, everybody kind of filters out. Feel free to ask me anything. Doesn't matter. Thank you very much. I appreciate it. No problem. Good luck on the test.